So welcome. So welcome to the seminar that will be hosted jointly by the Andy Thomas Center for Space Resource and School of EEE, Electrical and Electronic Engineering. It's a great honor to have Jason Rhodes from NASA Jet Propulsion Lab in Pasadena, California, to be here. Jason was born in Iowa in the US, and then he went to university to pursue his bachelor at Harvey Mudd College in California, which is one of the top liberal arts college that has the unique distinction where they produce perhaps the highest fraction of the graduate that end up with a PhD degree in science and engineering. It's a fantastic university. Then he continued to pursue his PhD at Princeton University. After his PhD at Princeton, then he went to continue with a postdoc fellow, a very brief postdoctoral fellow at NASA Goddard in Maryland, before ending up in Caltech, California Institute of Technology, and then later on with an 18 years career at NASA Jet Propulsion Lab. The talk that I'll be giving is about like NASA's plan for dark universe. Yes. So I think with that, let us actually welcome Jason, give him a warm welcome, and let's pass it to him.
Let me get this situated. Okay. Thank you very much for the kind introduction, and thank you everyone for coming. So I am going to talk to you today about NASA's plan for the dark universe. And don't worry, I'm going to tell you what I mean by the dark universe for those of you that don't know. But before I start with the talk, I want to thank a couple of people. One is Preston Dykes. He's a media specialist at JPL. He helped me and one of my colleagues put this talk together. We've given this talk as a team before, so this is the first time I'm giving the talk by myself. And the colleague that helped me put together the talk and I gave it to is Dr. Alina Kiesling. She wasn't able to make it here today, which is really too bad because Alina is actually a native of Australia. She's from Melbourne. She really wanted to be here today. And as the talk progresses, I'm going to tell you why she wasn't able to be here today. But this is the first time I've given this talk by myself without her helping. So bear with me if I struggle a little bit, but I'll do my best. So I want to first start to talk about the scale of the universe. And when I do that, I'm going to use some very big numbers. And a lot of people, in fact, a recent study showed 35% of people think that the numbers million, billion, and trillion are evenly spaced on a number line. But you're all technically savvy, and you're here at a talk about science, so you know that that's not true. But let's put these in perspective. If we thought of a number line that was about 10 centimeters long, and that represented 1 billion. The number 1 million wouldn't be halfway between 0 and 1 billion. It would be the width of a human hair. So if Alina was here, she could probably pull out one of her hairs and show it to you. I'm not so well equipped to do that. But a human hair is about 1/10 of a millimeter across. So that's about 1,000th of the way between 0 and 10 centimeters. So if we had this as a billion, we'd have a human hair over here at 1 million. And if we wanted to go to 1 trillion, we'd have to go 100 meters away into a completely another building. So these numbers are very, very different. The numbers million, billion, trillion are all huge, but they're not comparable to each other. And so I'm going to use those numbers at some points in this talk. So I want to keep in mind how big those numbers are. And I'll give you one more analogy here. So the analogy, if we think of a 10-cent coin as a million, that's our base unit here. And so if I was in the US walking along the street and I saw a 10-cent coin, I probably wouldn't bend over to pick it up. It might be dirty, whatever. If I was in Australia, I probably would pick it up because I don't know what the coins look like. So I think, oh, that might be a lot of money. But in the US, I'd skip it if I didn't want to get dirty or something like that. So it's a pretty inconsequential amount of money. If we think of something 1,000 times larger, that's $100. That's not an inconsequential amount of money. That's a nice dinner out for two at a restaurant. And if we think about another factor of 1,000 larger, 1 trillion in this case, that's a down payment on a house. Well, $100,000. Well, when we first wrote this talk, Alina and I, a few years ago, we thought, okay, that's a reasonable amount for a down payment on a house. As you probably know, here in Australia and in Los Angeles, it's no longer a reasonable amount of a down payment on a house. So maybe it's a down payment on half of a house. So, but you can see that these numbers, again, are very, very different, 1 million, 1 billion, and 1 trillion. So let's think about the scale of the universe, and what do these numbers mean? Well, our Earth, the planet we live on, about 1 million Earths could fit into our sun. And our sun is one of about 100 billion stars in our galaxy. It's a pretty average-sized star, so it's not a particularly large star. But still, 1 million of our Earths, these planets, could fit into the sun. 100 billion stars in a galaxy. And we think there's something like, of order, 1 trillion galaxies out there in the visible universe. So that's where these numbers, million, billion, and trillion, come from, or what they mean when we think about the scale of the universe. And so I'm a cosmologist. That means I'm a scientist that studies the contents of the universe and the evolution of the universe. And whenever a cosmologist gives a talk, almost, we start, or nearly the start, we start with this universe as a pie chart. So this circular pie. Now in the US, when I talk about a pie, it would be a pie with apples or something sweet. And I realize here in Australia, you could think of it as a meat pie, because I'm told that's what pie means here. But you can imagine this pie, and this pie doesn't have very even pieces. When I was a kid, you'd cut up the pie. You'd always want the biggest piece. Well, somebody's going to get sad if they're cut up this pie and they're given the small piece. But the pieces of the pie that we know the most about, that is the normal matter, make up about 5% of the universe. That's gas, stars, and these ghostly particles called neutrinos, about a billion of which pass through every square centimeter of you per second, but you don't feel them at all. But that's about 5% of the universe. And you'll notice there's a piece of the pie that doesn't even show up here, and that's planets. We think that every star has at least one planet, but planets make up such a small part of the universe, they don't even fit on this pie chart. So that's 5% of the universe that makes up the stars and the galaxies and everything that we can see in the universe. The other 95% of the universe is this dark universe that I'm going to talk about today. 27% of it is dark matter. That's a ghostly matter that we can't see. Light doesn't interact with it. It doesn't absorb light. It doesn't emit light, but we know it's out there. And I'll talk to you tonight about why we know it's out there. And the biggest component of the universe is dark energy that's causing the accelerating expansion of the universe. And we're going to talk about that too. So basically, we don't know what this 95% of the universe is. And I'm going to talk to you about how we're trying to study and learn about this 95% of the universe that's dark. So let's start here with the dark matter. How did we learn about dark matter? So I'm going to give a very brief history of dark matter here. If you look in the upper right, there's a scientist there called Fritz Zwicky. He did some pioneering work at Caltech, where I used to work before I came to JPL. And his work at Caltech was looking at the motions of galaxies. And when he looked at the motions of galaxies, he used the equations of motions that we've known since the time of Newton. We've known these equations of motion, how fast something should be moving based on how much force there is on it, and the force of gravity. He looked at these galaxies, and the motion of these galaxies told him that the galaxies were much heavier than they should be if he could count all the stars and the dust that he saw in the galaxies. And so he thought that there was something there, and we call this the dark matter, but it was just based on the motions of these galaxies relative to each other. So if you look a few decades further into the 1960s and 70s, there was a pioneering scientist called Vera Rubin. And what she did is she studied individual galaxies. She looked at the rotation of galaxies. And I'm showing an artist's picture of a rotating galaxy up here, like our own very Milky Way galaxy. And what you see in that galaxy is there's lots of stuff in the middle of the galaxy, stars. It's very bright in the middle. And as you go to the outer edges of the galaxy, there's a lot less stuff. So again, using the equations of motion that we've known for hundreds of years, she calculated what the rotational velocity of that galaxy should be. That is, how fast the galaxy should be rotating as a function of the distance from the center of the galaxy. And since there's less stuff in the outer edge of the galaxy, she expected, as all scientists did at the time, that the expected velocity would be lower in the outer edges. That's that dotted blue curve, A, that I'm showing in the plot there. But instead, what she found for just about every galaxy she studied was that the actual velocity remained constant into the outer edges of the galaxy. So what that means is there's mass in the outer edges of the galaxy. There's stuff there. We just don't see it. And this was the first really hard, direct evidence for this stuff that we call dark matter. And so, again, this was pioneering work done in the 1960s and 70s by this scientist. And in the ensuing decades, 50-some years since then, we've made lots of measurements that have, in fact, confirmed this dark matter, but we still can't see it. So how have we confirmed this dark matter? So I'm going to talk now about the growth of structure in the universe. And what I'm showing here is a baby picture of the universe. This is the earliest known picture of the universe. And in fact, it's the earliest possible picture of the universe for reasons I'm not going to explain now. But this is the earliest picture we can get of the universe. This is a picture of the cosmic microwave background radiation. This is radiation left over from the Big Bang. And this is the universe as it appeared about 300,000 years after the Big Bang, which occurred about 13.7 billion years ago. So this is very early in the universe. And what you see here is a picture of the density of the universe. And in fact, the universe at this time was very, very smooth. That is, it was almost completely smooth. But there were some spots showing up here as red spots where it was more dense, and some spots, the blue spots, where it was less dense. And what we're showing here is a very exaggerated picture of those density differences, where the density differences would be just 1 part in thousands. That is, very small differences in density. And in those over-dense region, the red spots where there was more stuff, there was more gravity. So stuff started to accrete in those regions. So where there's more gravity, there's more stuff, and you get a buildup, sort of an effect where more and more stuff is getting pulled in. And that forms the structure that we see today. When I talk about structure, I'm talking about galaxies here. So this is one of the deepest images ever taken with the Hubble Space Telescope. Every splotch of light you see there is a galaxy, like our own Milky Way galaxy, with hundreds of billions of stars. And so those overdense regions in the very early universe grew through this gravitational attraction to be the galaxies and clusters of galaxies we see today. But of course, you're only seeing the tip of the iceberg here. And so what I mean by that is when you see a galaxy, you're seeing the stars that are giving off light, but you're not seeing the dark matter. Just like when you see an iceberg, you're seeing the if you're above the ocean, you're seeing just the small part of the iceberg above the ocean. There's much more part of the iceberg that's below the surface. So when we look at these galaxies, we're seeing the regular matter, but we're not seeing the dark matter. And so I'm going to, in a minute, I'm going to tell you how we detect this dark matter, but I'm going to take a personal diversion here to talk about the growth of my structure. So this is a baby picture of the universe of me and Dr. Kiesling, who I mentioned before. So this is the first known picture of us together. And what you see here is it might look like there's no attraction like in the early universe, but there's definitely a very slight attraction there. And the reason I know that is about 8 years ago, we got married. So I'm usually giving this talk with my wife, as I heard a bunch of, oh, well, I'm going to get in a little trouble because I said about 8 years ago. And when I was setting up this talk, I didn't check dates. And so it wasn't about 8 years ago. It was August 9th that we got married. So I got in a little bit of trouble. Yeah, thank you for coming and doing this. But the reason Dr. Kiesling, Alina as I'll call her now, is not here is that last time we gave this talk was pre-COVID, and we started a new project during COVID. And Alina is with our new project, which is my daughter, who is 18 months old. And they're both in Melbourne visiting her grandparents, Alina's parents. So she sends her apologies that she couldn't be here today. So you'll notice on my daughter's chest, there is a shirt that says Roman Space Telescope. Remember that, because I'm going to talk about the Roman Space Telescope in a few minutes. And also remember the pattern that you see on that shirt. But I'm going to now go back to the science. and I'm going to talk about a technique called gravitational lensing. And this is the technique that we use to study the dark matter. So what I'm showing here is a very stylized cartoon-like picture of an observer with a telescope here at z equals 0. And z is just the units we use to measure distance in cosmology. We use kind of strange units. And so we look at a galaxy, a very distant galaxy. That's at a distance unit z equals 1. And you might think, well, 1, that's pretty close. It's a small number. But in fact, the way that this z units work, that's about halfway to the edge of the universe. So it's a pretty distant galaxy. So in the absence of anything between us and that distant galaxy, the light from that galaxy would take a straight path to us. But we know this dark matter is out there, this ghostly dark matter. And in fact, with this gravitational lensing technique, we're most sensitive to dark matter that's about halfway between us and the galaxy we're measuring. And one of the consequences of Einstein's theory of gravity, his theory of general relativity, is that mass bends space. So instead of taking a straight path to us through this dark matter, space is bent and the path of the light is curved by the dark matter. And I'm showing here a very exaggerated, non-scientific way of the path of the light being curved by the dark matter. But the effect is this. Instead of seeing the galaxy as it actually is, we see a distorted view of the galaxy. What was once a circle is now turned into an ellipse. So the change in the shape of the measured galaxy is what's telling us there's some dark matter there. And these shape changes are typically very, very small, 1 to 2% in most galaxies. And they're very hard to detect by eye. You can't see a big change in the shape of the galaxy. And we don't know what the shape of the galaxy was to begin with. So we're going to have to make this measurement of this lensing on lots and lots of galaxies. So what I've shown you here is a stylized picture. And I don't show you a picture of what weak lensing looks like on any one galaxy because I said the effects are very small. But sometimes we have so much dark matter that we have what's called strong lensing. So what you're seeing here, these very, very bright yellow spots, are parts of they're galaxies in a big galaxy cluster that's fairly close to us. And this big galaxy cluster has lots and lots of dark matter. So around some of those very, very bright yellow spots, you're seeing these streaks, what we call arcs. And what those arcs are, they're very distant galaxies that if we didn't have all this dark matter in front of us in this galaxy cluster, those very distant galaxies would show up as just tiny pinpricks of light on this picture. But instead, the gravity from the dark matter is bending space, and we're seeing these huge arcs. So again, this is evidence of dark matter out there. And the strong lensing here is one of the best ways we have to measure clumps of dark matter. But it's fairly rare in the universe. But it's not completely rare, and we have lots of images of these strong lensing. And here's one of my favorites, this strong lensing. So I think this is not Photoshop. This is an actual image that we took with the Hubble Space Telescope. And I think what this image tells me is that the universe is happy that we're trying to figure it out. It's telling us, keep going. So I'm going to use another analogy now to talk about how we use gravitational lensing to measure dark matter. So I call this analogy a penny in the pool. And full disclosure, while Alina and I live in Southern California, we don't have a pool, but we do have a bathtub. So this is actually penny in a bathtub, but I think it sounds classier to say penny in a pool. So penny is I don't know if you know, it's a 1-cent coin in the US. So we'll put this penny in a bathtub, and you know that there's water in this bathtub because you can look at the distortions of the shape of the penny. So in this analogy, the penny is like the distant galaxy, and the water is like the dark matter. You don't actually see the water in this image, but you know it's there because you're seeing its effect on the shape of the penny. In the same way, we don't see the dark matter directly, but we know it's there because we see its effect on the shape of distant galaxies. Now, if I have a pool and I throw in 1 penny, I'm not going to be able to tell very much about the water in the pool by just looking at that one penny. But if I have a pool and I throw in 1 million or 100 million or even 1 billion pennies into that pool, I'm going to be able to look at the shapes of those pennies, and I'm going to be able to deduce a lot about the water in that pool. In the same way, if we look at billions of galaxies in the universe, we're going to be able to deduce a lot about the dark matter out there in the universe. And so that's the technique that we're going to use with some of the future telescopes that I'm going to describe to you in a few minutes. So we've talked a little bit about the dark matter. Let's now talk about the biggest piece of the pie, the dark energy, that's even more confusing and strange, even to scientists like me who study it. So I'm going to throw up one equation here. So bear with me. I know I don't usually like to use equations in public lectures, but this is a very beautiful and striking equation for the following reason. This equation represents everything in the universe with one simple equation. So let's ignore the subscripts, the mu nu at the bottom there. Those just tell us where in time and space we are. On the left-hand side, we have the g, gravity, which bends space. That tells us about gravity. On the right-hand side, the first component we have in Einstein's field equation, this t, and let's ignore the prefix 8 pi that just makes our units work. The t represents everything that we can see out there in the universe, stuff, matter, and energy. And in fact, it represents normal matter and even dark matter, which Einstein didn't know about, but behaves the same way due to gravity. So at the time, about 100 years ago, when Einstein was coming up with this equation, they knew about stuff, of course, in the universe, mass, stars and galaxies, and they knew about gravity. That's what Einstein was working on. And they thought that the universe was just made up of gravity and stuff, matter and energy. But at the same time, they thought that the universe was static, not expanding or contracting. And the reason they thought that is because that was considered aesthetically the most pleasing solution to a universe. They said, okay, the universe must not be expanding or contracting. That would be weird. So Einstein, when he was coming up with this equation, said if I have gravity tending to pull things in and mass, then I need something to keep the universe from collapsing in on itself. So he added this cosmological constant, this lambda, the term on the right here. And that's the term that Einstein added to allow for a static universe that wasn't expanding or contracting to make his equations work. So he just added that term, and this equation worked. And then people started to do things to test this equation. And one of those people was Edwin Hubble, who used a telescope at Mount Wilson. And Mount Wilson is very special to me, and the reason is if I go out in my front yard in Pasadena, California, I can see Mount Wilson from my front yard. So you can imagine that it was darker back then in Los Angeles, and so Mount Wilson is not really useful anymore for making science measurements, but the telescope is still there. You can go tour it. So it's exciting for me to be able to see where some of this pioneering work was done, even from my front yard. So in the 1920s, Hubble used this telescope at Mount Wilson to study galaxies, and he looked at the motions of galaxies. He was trying to see if galaxies were moving away from us or moving towards us and how fast. What he found was pretty interesting. Hubble found, and it's shown in this plot, that the further away from us a galaxy is, the faster it's moving away from us in all directions. So all galaxies that Hubble studied were moving away from us. So if you look at this plot, on the vertical part, we have velocity. That's the distance, or not the distance, how fast a galaxy is moving away from us. And on the horizontal, we have the distance to the galaxy. And so what you're seeing is that as you go to the right, the galaxies are moving away from us faster and faster. The only explanation for galaxies moving away from us in all directions faster and faster based on how far away they are, was that the universe is in fact expanding. This blew Hubble's mind, and the mind of all his contemporaries. They said, wow, the universe is not static, the universe is expanding, because the farther away something is, the faster it's moving away in all directions. So over the course of the last 100 years, we've continued to make these types of measurements. most notably with the Hubble Space Telescope, obviously named after this gentleman. And what I'm showing here is a plot that's now a few years old, 6 years old, of the same types of measurements with the Hubble Space Telescope, where we're looking at the recessional velocity, that is how fast galaxies are moving away versus how far they are away. And one of the really exciting things about this plot, to me, is that all of Hubble's original data that I showed up there in the upper left fits in this tiny corner down here. So what the Hubble Space Telescope has allowed us to do, it's allowed us to look much further out into the universe. And in fact, it's confirmed quite well that the universe is in fact expanding. So Einstein called this his biggest blunder. He said in a universe that's expanding, you don't need this cosmological constant. So he was somewhat embarrassed that he had added this in just for the aesthetics of the equation without any scientific evidence. And towards the end of his life, he called this his biggest blunder. So let's talk about what it means to be an expanding universe. So for the decades after after Hubble did his work and found that the universe was expanding, scientists tried to figure out which of these two scenarios was most likely for an expanding universe. And what I'm showing here is just a cartoon where you have the past universe at the bottom and the future universe at the top, and the present where we are now in the middle. So on the left, I'm showing an expanding universe that expands for some time, and then under the force of gravity starts to collapse, and eventually would collapse in what we call a big crunch. Everything in cosmology is big. There's the Big Bang and the Big Crunch. Another possibility is an expanding universe that expands forever, but that expansion slows down over time due to the force of gravity. That is, the universe starts to expand, but it doesn't ever collapse in on itself, but it expands slower and slower till many billions, trillions of years in the future. It's expanding almost at zero rate, but not quite. So these were the two possibilities that scientists were trying to figure out, because these are the two possibilities for a universe that has gravity and stuff, matter and energy. So let's use an analogy, and I'm going to show the first two scenarios in the analogy, but there's a third scenario that people weren't necessarily considering. So the first analogy is if you throw a ball up, the ball comes back down. We've all done this. This is normal. This would be like an expanding universe that eventually contracts on itself. Another possibility, if I was strong enough, I could throw up a ball and it would keep moving away forever, but slower and slower. We see this, for instance, with rockets. If you fire a rocket up into the air fast enough, it escapes the Earth. And in fact, at JPL, we've launched some rockets out of our solar system completely. But once the rocket engine goes off, that craft is always slowing down to the force of gravity. So these were the two scenarios that people were considering. But in the late 1990s, scientists found a third scenario that actually describes the universe. It's as if you threw up a ball and it went away faster and faster and faster. So that's very different than our daily experience with gravity and doesn't make a lot of sense. And it's on the right here. It's a universe that not only expands forever, but as time goes on, the expansion gets faster and faster. We call whatever is causing this faster and faster expansion over time dark energy. And really, I like to say that dark energy is a name we give to our ignorance of what is causing this accelerating expansion. We don't understand it. We didn't predict that this was going to be the case. And in the 1990s, this is what two individual teams found. And we've had lots of evidence in the past 20-some years that this is the case. So let's go back to our Einstein's field equation. So again, we have gravity, which bends space. We have stuff and matter, matter energy here. But we need a term that causes the accelerating expansion of the universe. Turns out this term does it. So this cosmological constant which is the simplest explanation for dark energy. It might not be the correct explanation. It might not be a constant. It might change over time. But we had to reintroduce this cosmological constant to the equations in 1998 when we discovered the accelerating expansion of the universe. So Einstein's biggest blunder went on to win a Nobel Prize for these three gentlemen in 2011. So I guess if you're Einstein, even your biggest blunder turns out to be, one, correct, and two, Nobel Prize worthy. So now this is the equation we use. So let's recap what I've talked about with dark matter and dark energy. So the dark energy is a repulsive force. It tends to push things apart, makes the universe expand faster and faster. But dark matter is affected by the attractive force of gravity. This matter wants to pull together. So the dark energy affects the speed at which the universe expands. So it was expanding slower in the past, it's expanding faster now, and we think, if we understand dark energy very well, that it's going to be expanding even faster in the future. And dark matter affects how clustered things are, tends to pull things together, galaxies and clusters of galaxies. Dark energy causes everything to move away from everything else. Dark matter creates or causes objects to want to move together. So there's a push and a pull in the universe. The dark energy pushing things apart, the dark matter pulling things together. And we want to understand the interplay between those. And in fact, we're going to use the technique that I talked about earlier, gravitational lensing, to do that. So I'm showing here a movie on the left. This is an artist's recreation, a very stylized version. So on the right part of that movie, you see some distant galaxies. Between us and those galaxies, it'll play again. You see some ghostly dark matter. It's hard to see with the lights on, but it's there. And what it does is it causes this gravitational lensing, a warping of those background galaxies as observed by us. And about 15 years ago, some of my colleagues and I, we used the Hubble Space Telescope to make measurements of this gravitational lensing effect in a very tiny area of the sky. The area of the sky that we did this measurement in is about the size of the eye on a coin held at arm's length. So just that little tiny area of the sky, we used the Hubble Space Telescope, and we made measurements of the distant galaxies there. And we did that at various points further and further away in the universe. And what that allows us to do, as we go further and further away, we're looking further and further back in time. And we looked at how the dark matter changed over time in its clumpiness. And keep in mind that clumpiness of the dark matter is given by an interplay between the attractive force of gravity, which we think we understand, and the repulsive nature of the dark energy. So by measuring this dark matter, we are able to deduce some of the properties of dark energy. But as I said, this was done over a very, very tiny area of the sky because the camera on the Hubble Space Telescope is very, very small. While it's powerful, it's very small. It doesn't look at a big area of the sky. So in the past 15 years, my colleagues and I around the world have been working on 3 telescopes that are going to allow us to do these types of measurements over much bigger areas of the sky. And I'll mention these 3 telescopes now. So first telescope I'm going to talk about is the Vera Rubin Observatory. And keep in mind, this is named after that very pioneering woman in the history of dark matter. This is a telescope that's going to start operating in about 2 years on the ground in Chile. And it's got 24 countries making contributions, including Australia. So Australia is a contributor to the operations of this Vera Rubin Observatory, which is going to do a survey called the Legacy Survey of Space and Time. The second telescope I'm going to mention is a European Space Agency telescope called Euclid. And NASA is a big contributor to Euclid. That's going to launch hopefully next year. And that's going to do, from space, a survey of a number of galaxies that's quite large, over 1 billion galaxies. So we were looking at a few thousand with the Hubble Space Telescope 15 years ago. And now we're going to look at 1 billion. And the third telescope I'll mention is the Nancy Grace Roman Space Telescope. That's a NASA telescope that we think will launch in about 5 years. And one of the things I want to mention about both Euclid and Roman is they're going to produce lots and lots of data, take lots and lots of pictures of these galaxies. And one of the places they're going to downlink this data, they're going to send it down, is to New Norcia, which is an antenna that's being built just outside of Perth. So in all three telescopes, Australia is playing a really important role in making these happen. So I'll talk now about these three telescopes in brief and tell you some hopefully interesting things about these telescopes. I'll start with the Nancy Grace Roman telescope. This is a telescope that's 2.5 meters across, the same size as the Hubble Space Telescope, but much more powerful. It will be much more powerful than the Hubble Space Telescope, and I'll tell you in just a minute why that is. So why is it named Nancy Grace Roman? Well, who was she? So this was a woman who got her PhD in astrophysics from the University of Chicago in 1949. 10 years later, only a year after NASA was formed, she became NASA's first chief astronomer. And as NASA's chief astronomer, she championed space telescopes, the idea of sending a telescope into space. And in fact, during her time at NASA, she was known as the mother of the Large Space Telescope. That was a project at NASA, which once it got launched, was named Hubble. So she was really the person that pushed Hubble and made sure that the Hubble Space Telescope happened. And she got commemorated in a number of ways, but one of which was she's the middle one in this Women of NASA Lego set. She's standing there near the Hubble Space Telescope. But in my mind, since the Hubble Space Telescope is about the same size as the Roman Space Telescope, I'm going to pretend in the future that she's standing next to the Roman Space Telescope that's named after her. And while you can't probably read the disclaimer there, that's my employer NASA telling me, oh, if you're going to put a commercial product in your talk, you have to tell people that you're not telling them to buy it. So I'm not telling you to buy it. I do have 4 sets of this Lego, though. So you do what you want. So now I'm going to talk about why the Roman Space Telescope is so powerful. So this is an image of the Andromeda Galaxy. It's the galaxy nearest our own Milky Way. And a few years ago, one of my colleagues took some images of this, about half the galaxy with the Hubble Space Telescope, and it took 400 pictures with the Hubble, over 400, to cover this galaxy. With the Roman Space Telescope, which used to be called W1st, so let's ignore the W1st. I haven't had a chance to change this video. It will take just 2 pointings. So this is hundreds of times faster at surveying the sky, hundreds of times more powerful. And the reason is because it's got a huge camera. So this is a nice plot, I think, that shows the size of the Nancy Grace Roman Space Telescope camera. That's this sort of arch. That's the shape of the camera for various technical reasons. It's not a rectangular camera. It's this arch versus the largest camera on Hubble, which is there in the middle. So the Nancy Grace Roman Space Telescope has this camera that's 100 times larger than the Hubble Space Telescope camera. There are a number of other improvements that we've made with Roman that make that telescope about 1,000 times faster and better than the Hubble at doing these types of surveys. So if you see that arch of the camera, I told you, remember this. That's the same picture on my daughter's chest. So I have her out there most days. Some days we have to do laundry, but most days I try to have her out there advertising for the Roman Space Telescope. So the next telescope I want to mention is the Vera Rubin Observatory. This is a ground-based space telescope located in Chile. In the lower right, that's a picture of it being built. It's almost built. And what this telescope is going to do is it's going to take a picture of the sky with its huge, huge camera. It has a 3 gigapixel camera, and I'm going to talk about how big that is in a second. But it's going to take pictures of the sky every 5 days. It's going to take a picture of the entire sky in the southern hemisphere every 5 days for 10 years. And it's going to get great measurements of galaxies. And in fact, it will really make, by taking pictures over and over, it'll make a movie of the sky and how the sky changes. So we might think of the sky as very static, but there's lots going on in the sky with stars and even galaxies that's changing over time, and this Reuben observatory will be able to measure that. So as I said, it's got a 3 gigapixel camera. That's 3 billion pixels. So a very high-end digital camera has maybe 20 million pixels. And keep in mind, as we talked about at the very beginning, million and billion are very, very different numbers. So this will be the largest astronomical camera ever assembled. Just a huge, huge camera. And in fact, the camera itself is not something that would fit in a cell phone. This is a huge camera on this telescope, so it's going to be a very, very powerful telescope, this Reuben telescope. Euclid, on the other hand, has 2 cameras. So one camera in the visible, that is light we could see with our eyes, and one camera in the infrared. So that I'm showing here, just an image of a nearby galaxy, one in the visible, one in the infrared. So you can see very different things. So the reason this is exciting is that we're going to take a picture of the sky with the Euclid camera, both Euclid cameras at the same time. One picture will be invisible, and that's what we're going to use to measure the galaxy shapes for this weak lensing experiment. And one picture will be in the infrared, and we're going to use that to get the distances to the galaxies, which is another piece of information that we need to do this weak lensing experiment. So I find this particularly exciting because the Euclid camera is, each of those 2 Euclid cameras is twice as big as the Roman camera that my daughter wears on her chest. So these are huge cameras that are going to let us take pictures of many billions of galaxies. So who was Euclid, and why have we named a telescope after Euclid? Well, Euclid of Alexandria was a Greek mathematician. And for those of you that read Greek, I've put his name there in Greek. He wrote The Elements, which is one of the most influential mathematical texts of all time and was used as the standard mathematical text for about 2,000 years. So he's called the founder of geometry, or father of geometry. And very little is known of him or his life. Not a lot of contemporary records remain. But he quite famously is supposed to have said, there is no royal road to geometry. And what did he mean by this? Well, the king at the time was trying to use his textbook to learn about geometry. He said, this math is hard. Isn't there a better way you can explain it to me so I understand it? I'm the king after all. And Euclid said, there's no royal road to geometry. You just have to study. You have to do the work. So it turns out dark energy maybe determines the geometry of the universe. And this weak lensing experiment that I'm talking about, it's very challenging to measure the shapes of galaxies to the accuracy we need. It's very challenging to measure 1 billion galaxy shapes. So what we've come to realize is there's no royal road to understanding dark energy. We've got to make these measurements. We've got to build these telescopes. So I think Euclid is a fitting namesake for one of these telescopes. So the Euclid Consortium is about over 1,000 scientists and engineers around the world who are putting together Euclid. And we get together every year, or at least in person we did before COVID, and now we started to again this year. And this was our last in-person meeting before COVID. So this is a few hundred of the over 1,000 scientists and engineers working on Euclid. And one thing I like about this picture is I know the people in it, so I can pick out, hey, there's me and Alina, my wife. We're standing there in the picture. So I did that, and then I said, okay, who else from NASA JPL is in that picture? And I found them all, and there they are. You'll have to trust me. But I counted it up. This is the kind of thing scientists sometimes do when we have a mental block and got to take a break from our research. I counted them up, and I said, oh, wow, we're about 5% of the Euclid people in this picture. So obviously the people from JPL Pasadena are the normal part of Euclid, because we're the 5%. So I didn't tell my European colleagues that, though. So now I'm going to talk about a bit about why do we study dark energy. So the main reason we study dark energy is we have an intellectual curiosity to know about the universe, understand the universe, and that's why most of scientists do science. They want to understand the universe. But in fact, dark energy, as I've told you, will determine the ultimate fate of the universe, how the universe evolves over time in the future. And so what we think about, what we know about dark energy now tells us that there's a likely scenario for how the universe evolves over time in the future, if what we understand now about dark energy is correct. And I should stress that we know very little about dark energy. We'll know a lot more in about 10 years when these telescopes I've talked to are done. But our best guess now is that the universe is going to keep expanding, and it's going to keep expanding faster and faster and faster. Galaxies are going to move away from each other, and eventually the galaxies are going to move so far away from us that we won't be able to see them. We will, in fact, just be alone in our Milky Way galaxy, not able to see other galaxies out there. So it'll be a very lonely end to the universe, where it's just our galaxy. We can't see anything beyond our galaxy. And so I've tried to use this before. I've gone to NASA and said, oh, you've got to fund these telescopes. Eventually, I'm not going to be able to see these distant galaxies, so I need the funding. I need the funding now. We've got to build these now and do this experiment. And of course, they say, okay, well, when does that happen? I say, well, it's many, many billions of years in the future. So it has not been an effective way of getting funding, but it's kind of a lonely way to think about the end of the universe. It's just us and our galaxy alone. But it's not the scariest way to think about the end of the universe. So I'm going to talk to you here about a slightly scarier possible end to the universe. And so I'm showing here, it doesn't show up great. This is a campfire. So we have a tradition in the US of sitting around campfires and telling scary stories. And in fact, the first time Alina and I gave this talk, it was on a Halloween, so it was a great time to tell a scary story. So if dark energy is stronger than we think it is now, or it changes over time to become stronger in the future, we'll have a different future than the lonely single galaxy that stays together as a galaxy than I've described. About 60 million years before the end of the universe, galaxies would rip apart under the force of this dark energy. That is, stars would be thrown out of galaxies, and galaxies themselves would cease to exist. At about 3 months before the end of the universe, solar systems would rip apart. That is, the planets would be flung away from their stars as the ever-accelerating expansion of the universe due to dark energy caused the universe to expand faster and faster. At about a few minutes before the end of the universe, the stars and the planets themselves would be ripped apart by the force of the dark energy. And at the final moments of the universe, atoms themselves would be ripped apart. Electrons stripped from the atoms, protons and neutrons stripped away from each other. And in fact, the very fabric of space-time would rip. And as I've told you before, we obviously call this the Big Rip because we always like to say big in cosmology. So that would be the end of the universe if dark energy turns out to be considerably stronger now or in the future than we think it is. So that's why we study dark energy. We want to understand what the universe is going to do in the future. So that's the end of my talk. I really thank you all for coming, and I'm happy to answer some questions, and I'm just thrilled to be here. And I do want to say this is a particularly exciting time to be here in Adelaide because, as you know, for the last few years, Australia has had a space agency. And so I'm going to go to that space agency tomorrow and talk about some potential partnerships with NASA. So again, thank you for coming. And I hope I've given you a little bit of insight into the dark universe.
So thank you so much for your excellent talk, Jason.
Thank you.
It's good to see that we also have like partnership and collaboration with like existing collaboration with NASA, between the Andy Thomas Center and also School of EEE with the NASA Jet Propulsion Lab. So again, thank you so much, and we hope that we learn a lot. I hope everyone learned a lot about dark matter and the energy. And let's actually open up for a few Q&A, please. Please.
Go ahead. All right, so I had a great question, and I always hope I get this question because it's something I gloss over in the talk. So the question was, how do I know the image of the galaxy has been distorted if I don't know what the image of the galaxy was to start with? And the answer is I don't. And that's why I said if I look at any one galaxy or any one penny in the pool, I can't tell very much about the dark matter. So I need to look at many, many galaxies, thousands, millions, or even in the case of these future telescopes, billions. And what I look for is I look for coherent distortions in the galaxies. So two galaxies here will be distorted in the same way because the light is coming through the same patch of dark matter. And so if I look at many galaxies, I can look for patterns in the galaxies that are very small, but they're there if I have enough galaxies. So it's a statistical study. So one galaxy tells me nothing. A billion tells me just about everything. So that's a great question. I always hope I get that question because I do gloss over that. Yeah.
Please.
Thank you very much for your talk. I noticed that you didn't say anything about the James Webb Space Telescope. How do the telescopes that you show compare to that, and is there a reason why you didn't say anything?
Yes, there's a great reason I didn't say anything about James Webb. So I hope you've all seen the amazing pictures coming out of the James Webb Space Telescope. The reason I didn't talk about the James Webb Space Telescope is that it's got a camera about the same size as the Hubble Space Telescope. So it's going to look at very, very small parts of the sky. And so let me give you some perspective here. The whole sky is 40,000 square degrees. So I'm an astronomer, I know that number. You don't have to know that number, but everyone knows how big the sky is. Over the course of its 30-year lifetime, the Hubble Space Telescope has probably imaged about 30 square degrees. That's in 30 years, so maybe a square degree per year. So it's done less than 1/1000th of the whole sky in its whole lifetime. So the James Webb Space Telescope will be similar to Hubble in that it will survey maybe at most about a square degree per year. Whereas a telescope like Euclid is going to survey 2,000 square degrees per year. A telescope like the Vera Rubin Observatory is going to survey 18,000 square degrees of the sky, so almost half the sky, every 5 days over and over. So that's why I don't mention James Webb here, because it's not going to be a very effective way of measuring enough galaxies so that we can get this weak lensing experiment. It's going to do amazing things. It's already doing amazing things, and I'm actually really excited because this area of the sky that I mentioned, let me go back to it. This area of the sky, this tiny area of the sky that we imaged 15 years ago with the Hubble, we're going to go back in December. We're going to image that same area of the sky with the James Webb. So I'm really excited about that, but it's going to tell us a lot about galaxies, but not about dark matter. Mm-hmm. In the back.
So we see the universe expanding at the same rate in all directions, at the same distance. What does that mean about the shape of the universe or where we are in it?
So the question was, if we look at the universe and we see it expanding the same way in all directions, what does that mean about the shape of the universe or where we are in it? So the answer is very counterintuitive. And the answer is that every place in the universe is the center of the universe, because no matter where you are in the universe, if you looked, it's going to be expanding away from you in all directions. And the reason we have trouble visualizing this is we think in 3 dimensions, and what's happening is those 3 dimensions are actually expanding. So at any point in the universe, if you were sitting at any point in the universe, you would see it expanding in all directions, no matter where you were. So there's no real center of the universe. So we're not in a special place in the universe. Yeah. Yes?
Yeah, that's a great talk there. When you mentioned that dark matters or dark energy there, because of the light span there, is there any other possibility like a gray matters or gray energy will cause the same event?
So the question is there any other possible explanation for what we're seeing, I think, especially when we talk about the distortion of the galaxy shapes with the gravitational lensing? And the answer is, in science, there's always another possible explanation, But this explanation that we have a universe that's dominated by dark energy and the next biggest component is dark matter, that's the simplest explanation that fits all of the data we have. So I often see a story about somebody who says, oh, I can explain this observation with a different theory of gravity or something like that. But the theory we have here that I've portrayed is the only theory that fits all of the data we have so far. And I say so far because when we get all this data from Euclid and Ruben and Roman, we might find that our theory doesn't fit the data anymore, and then we'll need a new theory. But right now, this is our best theory.
Yeah. Oh, please, yeah.
I'll use the analogy of water. So water exists and has plenty of uses, right?
Yeah.
Dark matter exists. What are some of the uses that, or theories for its uses that you like?
So theories, I think you're asking me what are the theories for uses of dark matter. So there, we know so little about the properties of dark matter that I would say your guess about its uses is as good as mine. There was a Star Trek movie where the ships ran on dark matter, so as the fuel, I think. So it's really just speculation at this point because we know so little about it. And the real issue we have with dark matter is it doesn't interact with normal matter except through gravity. So it's very likely that if dark matter is made up of particles, which we think it is, there's dark matter particles passing through us all the time, and we don't feel them. So it's hard to capture dark matter for that reason. So it's hard to imagine how we would use it with our current technology.
Jason, you know that you are in engineering side.
Yes.
With that question.
Yeah, that's a good question. So what's the use? Don't know yet. That's for engineers to figure out. Yeah.
I have a question for the pie chart that shows the percentage of the matter.
Yeah.
So how do you determine the amount? It's like you need to know the overall amount of the matter in the universe already.
Yeah. So I think your question is, how do we determine how much stuff there is in the universe so that we know the size of the pie? Okay, that's a great question. So we know that this is, our universe is about 13.7 billion years old. If there was a lot more stuff in the universe, like a lot more dark matter in the universe, it would have collapsed in on itself a long time ago. So if there was a lot less dark matter in the universe, there wouldn't have been enough gravity to cause the clumping that we see that forms galaxies and clusters of galaxies. So the only way that we can get the universe that we see today with galaxies that, by the way, still exists because it hasn't collapsed in on itself, is by this amount of dark matter and dark energy. So otherwise, the universe wouldn't exist if this wasn't the amount. Yeah.
What do you mean by the end of the universe?
What do I mean by the end of the universe? So really, I'm talking about the end of the universe either being us in our galaxy, where we can't see any other galaxies, just for the rest of time. And time might keep going on for forever and ever. But we would eventually, all the stars would run out. And eventually it would get very, very cold. That's one possible end. The other possible end I talked about is space being ripped apart itself. But we don't really, I don't mean much more than that, those two scenarios of the universe growing lonely and dark or being ripped apart. So neither sounds great. So maybe that's another engineering problem for you engineers to solve is, can you find a way to manipulate the universe so that we have a different ending that sounds a little bit more palatable?
Are the distortions that you view of the galaxies consistent across time? So when you sample them multiple times, are they consistently the same distortion?
Are they consistently the same distortion? If we go back and look at the... Okay, so I think the question is, if I look at a galaxy now and I go back in a few days or weeks or years, am I going to see the same distortion? Is that your question? Okay, yeah. So the answer is usually yes, almost always yes, because galaxies are moving very slowly and change so slowly. But not always, and sometimes we have those strong lensing that I talked about. Sometimes if there's something happening with the distant, very distant galaxy, that it's moving slightly, then with the strong lensing we can see changes over time, on days, months, years, and we use that as another independent way to measure like the size of the universe. So that's a very exciting thing when we detect some change in the lensing. That's a very exciting thing because it's quite rare, and it means that something is moving quickly and is also very small out there in the universe. Yeah.
If the universe is constantly expanding, is it expanding into something, or how does the whole process of expansion work?
So another great question, and this question I get a lot is, I think I'll rephrase it as, what is the universe expanding into if it's expanding? And one of my colleagues answers this, says, oh, the universe is expanding into time. I don't find that a lot easier to explain. The way I like to say it is, it's not expanding into something else. There's not something outside the universe that is expanding into. It's just that we're getting more universe every day. So the universe is much, much bigger now than it was when I started this talk an hour ago. Yes?
So there's the 5% that we know a lot about, and there's the other dark stuff that we don't know a lot about. Where do black holes fit in all of this?
So black holes are part of the 5% normal matter.
But there's
Yeah.
still so much that we don't know about.
Yeah, so I should say the normal matter is stuff we know about somewhat, but we don't know everything about the normal matter. And I always have to say that because otherwise the rest of my colleagues in all other science fields who are not cosmologists would say, wait, what am I doing if we know everything about this? So we don't know everything about the normal matter, and we're learning a lot about black holes. But we think a black hole is just what happens when enough normal matter gets into a small enough space, it creates a black hole. And it becomes very weird. Our equations of physics completely break down inside the black hole, but it's not a different type of matter. And one of the theories for what the dark matter might have been, it might have been a bunch of small black holes out there, but if that was the case, those black holes would typically cause gravitational lensing. As something went behind a black hole, we would see it change its shape because there's so much mass there. And we don't see enough of that. We don't detect enough black holes to think that the dark matter is made up of black holes.
Also, sorry,
That's all right.
you mentioned that you have a talk tomorrow. Do you know if that's open to public, or?
Oh, no, I'm just having some discussions with your space agency. I'm not giving another talk. All right. But thank you for willing to come to 2 talks of mine. Wow, yeah. Yeah.
How do you think recent advances in plasmoid technology will help investigate dark energy?
In which technology?
Plasmoid thruster technology?
Plasmoid thruster. Okay, so this is I'm not familiar with that, but I'm assuming plasmoid thruster is a way of getting spacecraft, moving spacecraft. So I don't think that new ways of spacecraft thrust will make a big difference. And the reason is we're sending these telescopes that are going into space to a place called L2. That's the, for those of you that have done some physics, that's the Earth-Sun Lagrange point 2. It's just a place that's about 1 million miles away, and I shouldn't use miles here. It's maybe, you can convert to, that would be maybe 1.6 million kilometers if I did it right. But it's on the other side of the moon. So it's not that far. It takes a few months to get there. That's where James Webb Space Telescope is now, doing all its measurements. Euclid and Reuben will go there. So we don't need to send these telescopes very, very far away right now. There might be uses for that later if we, in a few decades, want to do even better measurements. And the reason is there's lots of dust in our solar system from the formation of planets. So if we were to send a telescope outside of the plane of the solar system, about 1 AU, astronomical unit. That is the distance from the Earth to the Sun, but up above the plane of the solar system, it'd be away from that dust, and the sky would be much darker. So the sky here looks dark, but there's actually a lot of light from dust still in these images. So if we could send a telescope far, far away outside of our solar system, then we would have a much better view of the sky. But that's decades away.
Hi, Jason.
Yes. Hello.
I'm asking this question from a physics teacher point of view. Today, actually, my colleague and I brought 15 students from high school, year 11 and year 12.
Thank you. Thank you.
Thank you.
Studying physics, of course. And I wonder what it takes to become a scientist at NASA. And I'm asking this question on behalf of my students, let's say. And I'm hoping your answer would be, it all starts from high school.
Okay. Well, obviously, I think I know it all starts from high school, but I would say it even starts earlier than high school. At least it did for me. By the time I got to high school, I was already very interested in science. And so I was reading a lot of science, and in science fiction too, but a lot of popular level science outside of school. But in high school, it's important to get the basics in physics, math, and other sciences. And then what I did is I went to college. I studied physics in college. I took only one astronomy course in college. And then I went to get my graduate degree, my PhD, also in physics. So it's quite easy to transfer knowledge from physics to astronomy. And so I didn't take very many astronomy courses in graduate school either. I studied physics, so I got a good grounding in physics and mathematics. But I loved learning physics. I loved learning math. And so college and then graduate school for another 5 years in the US. It's shorter some places. So there's 4 years of college and 5 years of grad school. That was a real joy for me. But you have to be in for sort of a long haul of lots of studying and classes. But one thing to keep in mind with graduate school anywhere in the world is you'll have some time that you're in classes, but then after that, you'll be doing research. So I was paired with somebody in graduate school to do research, and I got to use some of the very first data taken with the Hubble Space Telescope after it was launched, and so that was really exciting for me to get that opportunity. So yeah. Mm-hmm.
That one first.
Yeah. I like your shirt. His shirt says NASA, by the way. So I kept going. I hope the NASA guy asks the question. So.
You mentioned one of the other questions that dark matter could be a plug. And so I was wondering if you think you could learn anything about it from, say, like a particle accelerator, like CERN, at CERN, instead of
Certainly, we think that there are ways to learn about the dark matter particle with things like CERN or other ways of detecting dark matter particles. And I'm seeing one of the physics professors here right behind you who's studying that. So one of the things that's interesting about dark matter is studying dark matter. There's two very distinct ways of studying dark matter. There's what I'd say particle physicists do. They try to maybe create it in an accelerator or detect it in an underground experiment. And the reason it's underground is you want to shield against everything else. But then there's, so that would be the way to learn about sort of the particle that is dark matter. And so far, the consensus is that those experiments have not shown us the particle that is dark matter yet. But there's lots more work to be done. And the other way of learning about it is you study its astrophysical effects that I'm doing. So it's two very distinct ways of studying dark matter, but there are lots of ways that those two fields come together, and there's lots of crossover between those two ways of studying dark matter. Yeah. So why is dark energy called dark energy? And what is the energy? Was that the question? Okay, so dark energy was called dark energy by an American physicist named Michael Turner at the time of its sort of 1998 discovery. And I wasn't asked, so yeah, they didn't check with me. I didn't think it was a super great name because it might not be an energy. It might be a property of space itself. And so one of the interesting things is if it is an energy, it's not conserved. And so we all learn in physics about conservation of energy. But as space expands, if it's an energy in space, there's more space, so there's more energy. So energy might not be the right name for it. And again, I'll stress that dark energy was just the name somebody gave it, and it stuck. And it's the name we give to our ignorance of what's causing the accelerating expansion of the universe. So I don't know what it is yet. There's lots and lots of theories, but we don't know yet.
Maybe last question?
Yeah, so with the standard model, it splits matter basically into two sets of particles. You have force-carrying particles and matter. And one of the issues with the standard model is gravity, obviously. Would dark matter be another issue with the standard model? Is there something that the standard model doesn't account for at the moment?
Yeah, in fact, the standard model doesn't account for dark matter very well. Dark matter, as far as we know, dark matter only interacts gravitationally and not through the other possible forces. It's possible that it does interact through those, but if it does, it would interact very, very weakly because we don't see it interacting very much. And in fact, one of the possible explanations for dark matter particle is called weakly interacting massive particle, a WIMP. So kind of a funny name. So, yeah.
All right, we can go on and on for hours. It looks like the Q&A, but we greatly thank you and for this fantastic talk, and we learned greatly a lot about like dark matter and dark energy. And on behalf of John, Carlton, and I, we greatly appreciate this. There have been lots of collaboration between our school of AAA and Andy Thomas Center with NASA, and we believe that this partnership will continue, and hopefully we'll grow it further. But again, thank you so much too, also for having a lot of students here, including the high school students who are here. Thank you again, Jason.
Thank you. Thank you. Thank you very much. I'm happy to stick around if people want to come down. Yeah.
So you'll be